My name is John Mann, Director of Education for Lakeside. And to wrap up our theme week of artificial intelligence, today we are very fortunate to have Dewinder Carr with us. And her session is entitled Nature-Inspired Computing for Engineering Applications. Dr. Carr is a professor and graduate program director in the Department of Electrical Engineering and Computer Science at the University of Toledo. She obtained her PhD in computer engineering from Wayne State University in Detroit, and Carr's research interests are to develop intelligent engineering applications based on hybrid computerized models developed using nature-inspired and fuzzy systems. She has published upwards of 125 papers in reference journals and proceedings of the international conferences, and is a recipient of Commonwealth Scholarship, Thomas Rumble Fellowship, and Fulbright Senior Specialist Award, and visited Nippon Institute of Technology, Japan in that capacity. I would ask if you would please mute your cell phone ringers and help me in welcoming Dr. Dewinder Carr.
Thank you very much. It's my pleasure to come to this beautiful lakeside village kind of atmosphere and share some of my insight about nature-inspired computing. Especially engineers here do very technical things, and they never think much about nature. That nature itself is the biggest engineer, I would say. And I would like to share some of the things which we learn from nature and try to incorporate them in our design methodology. So having said that, so I come from University of Toledo, and this is our template, standard template, and we have a beautiful campus. We have that is an telescope there, and that is our main old building. It's all kind of a gray stone kind of old architecture there, and a little river also flows through. John is also a graduate from University of Toledo. So having said that, why we are looking for nature, or when I'm going to briefly talk about these things. So I'm going to talk about genetic algorithms, which are taking inspiration from nature. Swarm intelligence. Swarm intelligence, what is like? It is a behavior of all animal world, like a group of ants, birds, wolves, bats, bees, all animals which work together, okay? It's like a decentralized control, but how they communicate with each other and try to accomplish a big task. So it's called swarm intelligence. Fuzzy logic. Fuzzy logic, most of the word we know is Boolean logic. This is white, this is black. You are yes, you are no, 1, 0, 1, 0, right? But fuzzy logic we have like all the shades of gray between 0 and 1. Okay, so that makes more sense when we are designing things. For example, if we design like a height of the individual, if the height of the individual or the temperature, if you say if it's above 80 degree Fahrenheit, it is very hot. But what about if it is 79 or 82? It is very close to hot, right? And similarly, so in that sense, fuzzy logic is, so we will say that degree you are hot, if you are 82, maybe you are hot 100%, or if you are 81, maybe 90%, 79%. So there is a degree of truth, not just 1 or 0. And if we try to design our engineering models like many control system, so this is practically used in many elevator control. The elevator control is very smooth if we design like that. And other things we will give you some examples later on. But if you design based on fuzzy logic, your design is very smooth. For example, simple example is if you have your room, if you set your thermostat, okay, if the temperature is above 80, fan speed should be high. If it is below 80, the fan speed should be slow. So suddenly when it will jump from 79 to 80, you will have a big jerk. But if you design with fuzzy logic, it will gradually, smoothly change. That is the idea of fuzzy logic. Immunocomputing. It is based on human artificial immune system, we call it, that algorithm. So where, how we learn from how our body responds. So like whenever a foreign invader invades our body, for example, we had COVID, okay? So that is like how our body responds by creating antibodies to the invading antigen and tries to overcome it. So this particular algorithm is based on that. Okay, now deep learning, okay, this is it's an extension of neural network. Neural network is also a brain-inspired computing because it tries to model how our neurons in our brain work. Okay, they all work collectively, not because they take input from their surrounding neurons and then they fire if it is above a certain threshold. And deep neuron also is a kind of neural network which is specific details about certain feature selection, and we develop now these days large language models, long short-term memory. So it tries to follow the pattern in the changing world. So I think I covered everything. So evolutionary learning is like you can learn from all these objects. You evolve, okay? You evolve, learning. So you do not have initially any solution, but how you evolve and learn as the nature will do. I will just explain later on. So that's the inspiration. When you don't know the solution to the problem, what do? So you ask, how nature would do it, okay? So we have evolved from one single cell of amoeba to human beings, and how dinosaurs came and they are no longer there, how this evolution took place, okay? So it is based on that. So this is there's an institute, I don't know, maybe you call it's called biomimicry, and there is also asknature.org. You will find many examples they are trying to now introduce into high school students. So I would like to play this one. How will I play this? No.
And we realized, when there's an emerging discipline, where do you start to naturalize it in the culture and to build all the institutions that an emerging discipline needs? And what we said was that, ultimately what we're trying to do is take the ideas from the natural world, the wisdom from the natural world, and let it flow into human systems design of everything. And so we needed to create a flow structure. That's how nature would do it, right? Something that would easily flow from one to the other. And the most important impulse was to get people to ask, how would nature do this? And then once they asked, we had to make sure that they would have a way to find an answer. And that became tools like Ask Nature, methodologies about going outside and how you look and how you observe, ways to go through the biological literature. I called it, there needs to be some sort of an innovation matchmaking service, right? Because I realized that the people who make our world, the engineers and product designers, they don't take biology in school. It just doesn't happen. So they're creating a pump that's run by an internal combustion engine, but they've never learned about the whale heart, which is an incredible pump that pumps, 65,000 miles of arteries and capillaries. Biologists know about it, but the people who make pumps don't. So it was creating this place where biological knowledge and intelligence could easily be accessed at the moment of creation. That became asknature.org.
So, since I think I will first like to show here this slide. There are many products and material which are being developed inspired by nature. So here is like the lotus flower of lotus leaf. So the water doesn't stand on it, okay? It is self-cleaning. So how does it do? So there are many of these designs, like especially those people who are in chemical, nanomaterial design people, So on the right side is like the lotus leaves look very smooth, but on the right side is the detailed structure. It has very little contact, no, with this, so the water flows through it very quickly because very less resistance. Though they try to imitate these things and try to design new products like some fabrics where the water will simply slip away. So these kind of things they do. So elephant trunk inspired robot. So robots normally we go like they are very jerky movement, but they try to design robots which take inspiration from the trunk of the elephant. So it is less jerky, very smooth transition it does. And then on the other side, you can see the Velcro fabric was designed from those burrs of that animal, like how they are burrs and they try to attach to each other. So, and there are other things also, like when somebody was doing a research, I did not put it here, was taking from the maple leaf. Okay, they were trying to design a single wing helicopter, like how the maple leaf falls down. So they had designed that single wing aircraft. So there are many design things. So they can fall in like material design, chemical engineering, mechanical engineering. Since I'm coming here from the algorithmic side of the electrical computer engineering, I will focus about the algorithms which took inspiration. So that was this slide. So I'm going to briefly touch upon genetic algorithms. These have been there. Genetic programming, our neural networks, artificial immune system, swarm intelligence, fuzzy inference system, hybrid, like when we combine these two, like evolutionary neural systems, swarm neural networks, neurofuzzy, they combine neural network and fuzzy logic, grammatical evolution, you create a grammar template and then you use nature-inspired techniques to evolve that grammar template. So these are some of the things which I am going to talk about. So let's talk about genetic algorithms. Genetic algorithms are, in the biological inspired computing, they are the oldest one. Like they have existed for 20, 30 years, you can say that, the inspiration. So they take in, this is going to take, genetic algorithms is inspired by natural process of evolution, okay? So the foundation is Darwin's theory and Mendel's theory of genetics. They are based on that. So when we do not know the problem, whatever we want to find, we try to design it as a chromosome, okay? And we generate random chromosomes. And then we figure out what is the fitness of those chromosomes. It is also based on what they call the survival of the fittest technique. Okay, so we do not know the solution, we just design the problem. Like whatever we want to find out, that is represented as a chromosome. And then we initial body of chromosomes, we cross over, chromosome produce next offsprings, evaluate their fitness, survival of the fittest people try to get more opportunity to reproduce. And so this is based on that ideology, okay? So this is like the flow graph of a genetic algorithm. So we have create a population of chromosome. But how do you define a chromosome of a particular problem is based on what we call as formatting a chromosome of a particular engineering problem. So determine the fitness of each individual. Those who have higher fitness will get selected most likely. And then they reproduce by crossing over like human beings do. We take equal number of genes from mother and father, crossover, but in this algorithm, the crossover point can be anywhere. So you do that, perform computation, crossover, then you also, when you are doing reproduction, there is some kind of a mutation, like we find some children who are born with some kind of a disability because some of the gene in the process gets mutated. And so that mutation is also a normal thing in the genetic process. So in human beings, we think mutation is not good, but in crossover, if we see the mutation operation is a very good thing, and we try to mutate it more so that we can maintain the diversity of the solutions. So this is like two parents crossover, and then crossover point, children are born, and that roulette wheel is the methodology which we use, like how to select the fittest chromosome. So it's like a roulette. Each chromosome gets an area on that wheel according to its fitness. So when we create a random number between 0 to 100, so it's most likely it will stop there where has more area of the pie. So that is how we select or implement survival of the fittest. So fittest chromosomes get more opportunity to reproduce. Like if there is, may know if foxes, they have to run. So those fox who can run faster, that is their fitness. Those who cannot run that faster, the rabbits, those who cannot run, the fox will eat them. So it is like that, survival of the fittest. So these kind of things have been incorporated to evolve genetic algorithm. So then I am going to talk about genetic programming. So in genetic programming also we take this particular inspiration, but we try to evolve. Like here it is a small example which I used to give an exercise like X input and Y. So we know this is X, this can be a multi-input thing, and we do not know what is the formula for it. Okay, so we will generate a function which exactly matches the input output. So this is called grammatical evolution. That means we are trying to evolve a grammar, and we give ourselves some parameters, like we want to evolve this grammar template using that depth of the tree should be 4. We only want to use plus and multiplication, and we terminal set, we only want to use our expression having 0, 1, 2, 3, 4, 5 and X. That kind of thing is called the grammar template. So this is also a template of the flow diagram of the grammatical evolution. We create random binary string, integer string, we extract rules, program. So in the biological side, we are imitating this process, genetic process, transcription, translation, creates an amino acid and a protein. So now I would like to give you an example. There is later on in the slide we'll give you an example of that. So about swarm intelligence. So we have these algorithms called, they have decentralized control. Nobody is the boss. They are all working together, communicating with each other to find something. So like ant colony optimization, okay, ant clustering algorithm, particle swarm optimization, okay, these kind of algorithms, and later on more ones. It's like a collective behavior in the animal world, which is we observe to develop algorithms. So for example, ant colony optimization. How we have a swarm of ants. So if there is a nest and there is a food source, okay. So if one ant goes and finds the food, so when they are coming back, they put their pheromone or their scent, okay. So when other ants go, they smell their scent, okay. And if they go that direction, they also find a food. They also come back and deposit the pheromone. So, and those ants who do not find the food, they don't deposit the pheromone. So this way, initially they don't know if the ants go everywhere, okay? Once one find a food, you will see slowly everybody goes in that direction. So that trail from food to the nest becomes very strong. So, okay, this is like they are all communicating through pheromone, okay? So they find the shortest path from their nest to the food source. So this is the inspiration, so we model those things like that. And clustering algorithm is based on how the ants are trying to collect their dead bodies. Okay, they pick up their dead bodies, put in small cluster. From that cluster, they try to put at a big cluster. So they try to pick up the dead body from where it is scattered to some place where it is all collection. So that algorithm was based on that. So particle swarm optimization. So the earlier one is like birds, how they try to fly in a flock and a beautiful formation. There is usually one bird which is the leader and all others are trailing behind, okay? But that leader is not a permanent one, It changes. Nobody is permanent leader. So that algorithm and so that is based on who is the global leader, who is ahead, and who is their local leaders who are nearby. So they try to estimate their positions from the local best and the global best, and thus try to adjust their position so they maintain their flock and they navigate. So those algorithms are based on that. So this is something like I'm trying to say honeybee collection. Okay, ants also, how they try to find out which is the best nectar source where they have to make a hive. So they also have their own algorithm. When somebody finds a good nectar, they come here back to their nest and they try to do what they call stage dance, and from that dance it reflects whether the source was good or not. Okay, so this is like ant colony, and that is the birds flying. And there are many small robots which are doing this algorithm, and they collectively try to do that in the engineering world, which is taking inspiration from the particle swarm optimization algorithm. So these are some of the modern ones, like the gray wolf hunting algorithm. So they know how gray wolf hunt together in a group. It is based on that one. And cuckoo search algorithm. Cuckoo search algorithm is based on the cuckoo bird in the nature doesn't want to hatch her eggs. So she tries to look around all the nests and try to deposit her egg in that nest where it cannot be picked up easily. So it resembles to their local nests. So that algorithm is based on that. So we have a firefly algorithm, bats algorithm, Harry's hawk algorithm, you name. These are various other algorithms which are inspired by nature. So, and this is the artificial immune system, like your body is like an antigen who invades your body, and your body is trying to create antibodies in response to that, and that is like a lock and key arrangement just to nullify the antigen. This is how you try to defend your thing. So these are the inspirations. So this is like immune system is based from the human immune system, protects the body from external agents, foreign agents, which we call antigen, and then we create antibodies. There are two kinds of immune system, T cells or B cells done in bone marrow or thymus. So that is a little detail from where they take this information. And this is the flow diagram for a clonal sexual algorithm. We try to define here the problem as an antigen, and then we try to initial P antibodies or number of 50 n number of bodies in response to that. And then we see out of all the antibodies how their fitness improves. If somebody gets a better than antigen, we replace in the next generation, that becomes that antibody, the fittest one becomes an antigen for the next iteration, and then we go on till we find the solution. So here we try to, just giving you an example, how we try to solve the problem of what they call traveling salesman problem. It's a very unique problem in computer science, which means you are going to travel all the cities. Okay, you have to visit all the cities, no city twice, but you have to do it with the minimum distance. Okay, that is the traveling salesman problem. And as you can see, if the number of cities are very large, then you may try to go to the nearest city, and from there to again try to go the next nearest city. So that's called the nearest neighborhood method. So there are many methods. This is a very, very standard optimization problem in computer science. How do you optimize? So this particular problem, we solved it with this thing and compared it with other algorithms. So I'm just trying to show you this graph. So this graph, if you try to go the distance from this node, simple weighted graph with 6 nodes, that means it's telling you the distance. So some of the distance is 73, and if you take that route, the distance is 58. Okay, so depending upon which particular route you go, the total tour distance is affected. Like the middle one shows 73, the third one shows 58 distance. So this is so we try to implement the problem here as an antigen, the tour distance. If the tour distance is of 30 cities, we have a 30 cities antigen. Initial antigens, you go from 1 to 2, 2 to 3, that's initial, but then you say all other antibodies to it. And then we compared it with that, like 30 cities, 50 cities, 70 cities, 90 cities, and we have all these algorithms branch and bound, genetic algorithm, clonal selection algorithm, and the last one you see for 30 cities, we got the distance of, is this the light shining or no? 17.97. This algorithm gave us the best result. Okay, so this tells you like how we can do this optimization problem. So it was the best performing algorithm, much better than GA, and all other algorithms give you much better result than the conventional branch and bound. So now I'm just trying to take this other nature-inspired algorithm, which is like a neural network. This is how they define. Each is a neuron. It takes input from the neighboring brain cells, and if it is above a certain threshold, it fires and communicates to the next layer of neurons in the brain. So here everything is connected, everything. So we try to develop here a simple neuron, and I was saying this technique. So you can evolve, there were standard algorithms, we can evolve neural networks using genetic algorithm or swarm intelligence. These are developing a hybrid kind of algorithms which we have done. So here is a simple example. That particular top neural network is developing an exclusive OR gate. Okay, so if we try to evolve these gates using genetic algorithm, if we represent that whole neural network as a chromosome, like gene 1 weights of the connections which are connecting the neurons and some threshold, we try to, we found that if we use genetic algorithm, our program converged very fast, less number of generations, and took less time to train the network, and we got the same result. This was, of course, a very small problem, initial problem, but we have done greater other problems. So this is now the example of deep neural networks, where we have several layers of neurons and all neurons of a different layer. So this is very good for using image processing, called a convolution neural network. And this is called long short-term memory, which is network which is specially designed with the cells so that we can train the data, it can remember the trends in the data. So this kind of research work we did during the COVID days, that we try to see like how will be the number of new COVID patients depending upon the prior history of 10, 20 or 25 days or whatever we call the window size. And we got very good result. So if the trend is going up or down, it tries to capture the trend. So that is a special cell which does that. And we can also design it. And now there's a new model called transform models, which is used for large language models. This is also a model of our neural networks with self-attentions, and we can, like, for example, if you are saying few words, it will predict the next sentence and next word in your sentence. So this is also a model, and we can use bio-inspired computing techniques to optimize the architecture of these networks. So, so this is a little detail about transformer networks. I don't want to go into these details. So in general, what we call artificial intelligence, this is a global artificial intelligence. Then machine learning is a subset of AI. And within machine learning, we have shallow networks, and then we have deep networks. And so deep networks, no, they have many layers. That's why they're called deep neural networks. So I'm just trying to say some of the practical applications which we have used, and this is called intelligent energy management system using natural computing. So we know the demand for energy has been increasing over the years, and now we are saying the demand is rising, and we are now, of course, now facing that we have got this price of electricity is charged by the hour, and previously it was not down to consumer level, but now where I live, we have this hour of the electricity changing, like for example, they say don't use your air conditioning between 2 p.m. to 7 p.m. No, the price of electricity will be higher. So previously it was all the same, but now they do, right? So the idea is like, how do you do the energy management? The idea is that we need a smart grid, of course. Now we try to have we want to save money for us, but in order to say it in a very simple fashion, we would like to store the energy. And many people are also now integrating their household with the renewable energy, like solar panels or wind energy and other things. So the idea is, so like if you have multiple sources from energy, then how do you decide that when to use the energy from the grid or from the stored energy from the renewable energy sources, so that your total power cost is small? That's the main idea. Okay, so we want to do is there any algorithm? We don't know when to use. So what we do, so there is a price of the electricity changing every hour, okay, and how should we minimize? This is the problem, optimization kind of problem. So how do you do that? So there is no formula which tells me y is equal to this 4, 6, x square plus 3x minus s. You do that, okay? So there is no unique formula. So for such things, we need nature-inspired computing. So I'm going to share that with you. Because renewable energy storage, we have a smart meter. It does two things, this kind of energy. It saves price for you, and it also lowers the load on the grid. Because when everybody is in the evening time, the load on the grid is too high. The grid may not break down, like, so that it solves two function. So the smart meter is one which communicates, which tells you what is the hourly price at that time, and whether you should be able to, what is the demand on the grid. Of course, these are some of the devices which we know we need a two-way communication. Smart meter we have to have in the house, and then our thing is to reduce the monthly thing and also to stabilize the grid. So the prices are set a day ahead usually, and so with this particular, we worked on a data set and we try to implement. So the time of the day, whenever the time shifting price is high, we would like to not use that energy. Like this is the price of the electricity in a typical day. Afternoon it is high, and at night it is low, okay, and the demand is also less. So we simulated that in this you have got a two-way smart meter, and you need a communication link, Zigbee network. In this thing we imagine that we have that. So smart meter, energy storage unit, we assume that you have in your household. And then how do you do that? So this is the network, private area network, where we can require so that we know what is happening. So again, this is the genetic algorithm. We try to solve this problem using genetic algorithm. And these are the functions which you have seen before. So how do you propose this problem? So in this particular thing, just to say, so there are 24 hours in the day. So we model the problem as a 24 bits chromosome. Okay, we do not, so our one, so and what is the chromosome thing? It is telling you the state of the electric storage unit, whether you should charge at that hour from the grid or you should discharge the grid. Okay, so that is the thing. Each chromosome will tell us that, and then we evolve the chromosome. Okay, so like this is the problem, x1, x2, x24. Why? The problem says, this is a formulation of problem, because there are 24 hours in the day, and the problem is like x1, it will tell me if that number is positive, we are charging from the grid. If the number in that bit is negative, from 0 to -1, then we will say that we are discharging. It's 0.7, 0.3, 0.3% charging or 0.7% discharging, okay? So that kind of chromosome we want to evolve, because we don't know any formula or So this is the thing, so we try to do, and I would like to share some of the results. This was so we try to make an objective function which says that we should be able to always serve the demand in the household. We don't want to say, okay, you can't do laundry at this time because there is not enough power. No, all the demand of the household has to be met, and we have to also, like xn is 1 or greater than 1 we are charging, okay, or so we designed an objective function which is saying that we should not violate any of the constraints, okay. So if we did that, we implement that. This is objective function for 24 hours of the day. What is the load? What is the price at that time? And we have to optimize that. And when we did that, so I would like to show you the result. This was our result. The bottom slide, of course, that is our training algorithm of the thing. But the bottom, you see, graph is this 24-bit bar graph. So like in the hour first, it is going down. So we are discharging there, okay? So because, and then when it is up, we are charging. And the whole thing is from 0 to 1 or 0 to minus 1. Minus 1 means 100% charging, and it's not completely charging. This I think 0.9, and then whenever it is upwards 0.3, that means 0.3% we are charging from the grid at that time, and 0.5% whatever this discharging. So this is like a 24-bit chromosome. It tells us, because at each day, because price ahead every day changes. So for each day, and whatever price energy you stored in one day, you have to use it in that day, because next day the price will vary. So this is the particular example which we evolved, for which I don't believe there is any standard mathematical method of doing. So by doing this in this way, original cost would have been this, and with the GA, because we here GA1 we call it because we maintained that there was energy storage unit of certain capacity, and GA2, so we saved this energy cost by 29%. And if we try to do GA cost 2, that means if we increase our energy storage capacity, then of course our capacity, our savings increase, and so that of course was expected. So in order to test that, we use this data, because this was one of the projects which some graduate student did. So this is the kind of data we used, what was the price in that day, and we built this thing from there. So now I'm going to talk about this grammatical evolution which we talked about. We are trying to design the grammar template, and in this case the grammar template has been designed used for this iris data, right? Iris flower. So iris flower, is a unique flower. So sepal length, sepal width, petal length, petal width, these are the characteristics, and it has got 3 classes. It's a setosa, versicolor, and virginica. These are the 3 classes of the iris flower. So, but the question is, how can we classify based on these 4 inputs of sepal length, sepal width, petal length, which category is that? It's not very obvious, because all these there's no clear-cut case. So this length and width, they are all overlapping. So we have to take all these 4 inputs together. So in this case, we use fuzzy logic, and we design a grammar template. So I said Boolean logic is black and white, fuzzy logic is all the shades between 0 and 1. So this is the fuzzy logic model, which is the rule-based model. And this slide you have seen before. We create a binary string of numbers, and for each 8-bit numbers we can create a digit, which you will see here later on, and with this algorithm we come up with this tree structure, so we have like the same binary number, we convert them integer, like the red one is 104, and we apply to this grammar template. It says if sepal length is ant means antecedent, and sepal length is antecedent, petal length is so antecedent, and then what is the consequent. So all these antecedent and constituents we have to find. So ultimately by using this process, we found these 8 rules which classifies all the flower data in up to a very good accuracy. No has been done as a 100% accuracy, but it's very close to like 98% accuracy. So if sepal length is large and petal length is large, no matter what it is, always it is virginica. Only these 2 parameters matter. So rule 4 says if petal length is small, then it's definitely cetosite, came out from that. Other parameters do not small. So how this large, small thing, they were all expressed in fuzzy logic, which is, so now I'm trying to talk about cuckoo search algorithm. So this was also an algorithm for a scheduling problem. So scheduling problem, let me say, so cuckoo bird, I said you this is like tries to find a nest where she can deposit her egg, so she doesn't have to hatch it, and it is not identified by the other bird, otherwise she will throw it out of her nest. So that is the strategy we use. So goal is, okay, so I'm now going to define the problem where we have to use this. So this is like a generator scheduling problem. This is a electricity utility company, and let us say this is the data, this is what it is. So we have got 21 unit, there are 21 generators in electricity utility company, and each one has this capacity, like one has 555 megawatts. And then we have to do their scheduling maintenance. It is required for maintenance, no, 7 weeks in a year it has to be down. And then on the right hand side it tells you the manpower needed, because it has to be down for 7 weeks. So in the first week it requires 10, second week 10, then 5, 5, 5, 5, and the last week 3. So similarly for the second unit, 180 megawatts capacity, it is to be down for 2 weeks, and the manpower capacity needed is 1550. And these first one, they have to be scheduled, maintained in the 1 to 26 weeks, and the last ones have to be 27 to 52 weeks, okay? So this is a very unique thing. How do you schedule? So for their maintenance, okay, you can do that. But the thing is, in this scheduling, manpower demand has to be met. They have to be doing 126 also. And the idea is, how do we have to always, the net reserve of the electricity should be maximized, optimized, okay? So nowhere in our scheduling thing, situation should not arise that we are not able to meet the demand of the load, okay? So this is not a unique problem. As you can see, there is no clear solution there. How will you do that? Everything is, so all these constraints have to be managed. So how do you do? So we did this problem with the cuckoo search strategy. So first, so we define, because, okay, now here it is a nice thing. What was the nice thing? I want to go back. Yeah. So otherwise, if we don't use that, you see the total search space would be 26 raised to power 20. So many solutions if you want to try everything. So you can't do that. Since there are 21 generators and each generator can start at maintenance one of the 26 week, you do this problem. So the number of solutions grows exponentially with increasing number of generators. If you have the 21 generators more, you will not be able to do. So you have to come up with alternate ways. So we told you about this thing. So I just want to show the results. So we got this register with the cuckoo search algorithm. Okay, so it said week number 1, generators in maintenance 4. So which generator and which week the maintenance should start. And this is how we say how much power they generated. These are the results, but I want to show you the graph towards the end. So we compared it with all the other methods, and this integer cuckoo search algorithm, which is highlighted in the yellow, gave us the best result. It did not do any violation. So it tells us, like in this graph, generator unit 1 should start in week 2. Generator 2 should start in week 7, And of course, it starts from week 7, it will go through the maintenance cycle, which was there in the graph. It is supposed to be down for 5 weeks or whatever, it will do that, and whatever manpower it needed, that should be also there. So basically, how do we do that? We again defined a objective function which taking into all these constraints. No constraint should be violated, and if it violates, some solution violates, we penalize them and successively so whole problem of 21 unit was declared as a 21 bit cuckoo. We call it a cuckoo. Okay, so it's a 20 because that is our problem is 21. So we try to find the solution which will be in the form which generator unit should be started on which day. So if the pin is 5, generator 5 should be started, whatever the number is there, it should be started like here it says 6 should start in the 9 and then go from there for the whatever weeks it is supposed to be doing. I think so it gave us very good, and there was no violation as compared to all the other algorithms. So, and this is like a hunting behavior of gray wolf. We have alpha, beta, delta gray wolf. They hunt like together in a group, and we call alpha wolf is the one which is very close to the prey. They try, so this is the whole thing. There is a complete algorithm, and we here try to generate this thing, again integrating solar panel and a wind turbine. We assume this is the 4 kilowatt solar panel, and the energy storage unit in the house is like 15 kilowatts. And we try to, again, this is from a different data set. So our problem was like here a 24-bit state of charge. Okay, so whether we are discharging, so it's very similar to the same problem, but it is a different data set from Chicago, Illinois area home. We got this diagram which tells us how much, again, no, this was a different, of course, objective function. And we have to meet all the constraints, all this work, I think. So the bottom line is, when we use this strategy, how much cost we save. With the red is the cost with ESU scheduling with the gray wolf optimizer algorithm. So, and we can say that whenever there is a fluctuation in the prices more, then our algorithm works very good. If the price is flat, then of course there is no need of algorithm. And this is a comparison of this gray wolf algorithm over the other standard particle swarm optimization algorithm. And this may, whenever the month and January, so we try to, wherever there's more fluctuation, then there is more saving. So towards the end, I would just like to leave with this. This is also a YouTube video from a simple boy talking about nature.
3% of your life will be spent indoors. It seems like a lot, right? Look at us. Here we are, stuck inside. Bright light shining, but not sunlight. I've been wondering, if we spent all this time indoors, what lessons are we losing from the natural world? What are we missing out on? Well, today, I'd like to talk to you about the very real connection between humanity and nature, but also the disconnect between the lives we lead and the natural world. Have we lost our connection to nature completely? From my experience, there are 3 lessons I'd like to share. The first is that I believe nature's like a parent. You exist because you have parents. They took care of you when you're sick and helped you learn new skills. The human race itself has a parent too, nature. Really though, when you think about it, nature's the one who gave us herbs and berries to eat, and plants to use in medicine. So what if we didn't have nature? I mean, is it really that far from reality? Children today spend half as much time outdoors as their parents did. If nature's a parent, then why are we so afraid of it? Have our thoughts and ideas about parenting changed so much over the last few generations? The second lesson I'd like to share is that nature can be like a teacher. I remember When I was about 4 years old, I stuffed worms in my pocket because, well, I don't actually really know why. But it was still a valuable lesson because that was the time I learned worms would dry up after you put them in your pocket. How else does nature teach us? Well, a study from Norway has found clear associations between the extent of children's outdoor play and their ability to make progress in school. Playful engagement with nature, such as tree play, exploration, and child-initiated learning, is associated with many soft skills that are important for school success. And playful engagement also helps children develop their executive functions. Executive functions are a set of mental processes that enable us to plan, prioritize, filter distractions, and more. And unstructured play, like camping, biking, and swimming, also allows children to explore and practice setting and accomplishing tasks on their own. I remember when I went on a road trip which took me across Saudi Arabia. We stopped and camped in multiple destinations. We went to Taif, camped on the coast of the Red Sea, and other places, who knows where. It's all this time spent outside, camping, exploring, tuning over rocks, staring at the stars, that I know has made me the student I am today. The final lesson that I'd like to share is that nature can improve our health and well-being. Camping, biking, and swimming also help with both mental and physical illnesses. Nature is an important way to keep healthy, which is why doctors are now prescribing ecotherapy, nature-based programs and exercises that can help patients cope with mental and physical illnesses, such as anxiety, depression, diabetes, and high blood pressure. Simply listening to chirping birds, glimpsing the sky, and even noticing a tiny insect can all boost your mental well-being. If just looking at the sky can boost your mental well-being, why aren't we spending more time outside? Why have we lost our connection to nature over the last few generations? And I wonder, what would the effect of this disconnect to nature leave on our society and the younger generation among us? I'd prefer that you'd all take note of the 3 lessons I've shared with you today so that we can reclaim our connection to nature. Remember, nature's like our parent. It takes care of us and provides for us in the similar way my parents have provided for me. Also, we can learn many lessons from nature. I'd imagine that the lessons we can learn are endless. Finally, nature can heal us. Being outside can improve our mental and emotional well-being, not to mention our physical well-being. So why aren't we spending more time in nature? This is what I leave with you right now. Go outside and enjoy nature as it is. Feel the connection of nature in your everyday lives, and enjoy nature with your family as often as you can. Simply put, get outside.
Thank you. That was the end of my slideshow. Thank you once again. I don't know, I feel very passionate about this subject, and I believe you also got a little new perspective of looking at problems today. Maybe if you are, some of you may be already aware of it, some of you may not, I don't know. So I thought maybe if you can ignite your little curiosity towards nature. Any questions you might have?
To be able to follow up in general with the themes of different nature aspects, whatever, that are used for algorithms. Is there a resource for the pedestrian that you could recommend?
Okay, so these 2 resources are very good, kind of asknature.org and biomimicry. So this slideshow, I know you can find many video clips, and there are certain programs where in high school level also they try to introduce biomimicry. So you can find many topics. I just chose these 2-3 things for 2-3 minutes so that you can get a little exposure. But you will find many videos. So like I shared with you like um, the algorithms which we have implemented along with my graduate students and what work we have done. Some of them I have shared within this time constraint. So those kind of articles like, I was saying, a gray wolf algorithm or cuckoo search algorithm. So these kind of very that we find in like a journal publication like IEEE transactions on evolutionary computing, okay, and things of that nature, or International Journal of Intelligence, machine learning and things of that nature, okay. So those will be like more like research oriented. How did you solve the conventional problem with this technique, and how did you compare this result with other existing techniques so far? So how do you claim that your result is better than others? So that's all the scientific thing. Yeah. So technical thing with this, but I think asknature.org and biomimicry. Here you will find a lot of video slides, video lecture series, and what programs they do at high school level.
Thank you. Thank you.
There was a hand here. Okay. Sorry.
Hi. Yes, I had a kind of a two-part question. The first part of the question is you presented a number of examples where these types of nature-inspired algorithms have been employed in problems like logistics or problem solving. Do you see this as a growing field in machine learning and AI? That's the first part of the question. Or is there something else that is gaining popularity instead of these nature-inspired algorithms? And the second part of that question is, what's the barrier that is keeping these types of algorithms from being employed in more widespread applications in engineering and science?
So the first question you said is, I shared these algorithms and where we have done some research work. So I shared, that's one thing. So so you said this is of course evolving the area, but this is not the only area evolving in machine learning, because machine learning previously we had simple neural networks, okay, when they came. Somebody proposed the idea, I think in 1956 and 70, but basic idea of neural network. But at that time, the computing platform was not that powerful that they could not implement and get the results. So then later on, after in the late 80s, when most of the universities will have desktop computers available, so then this neural network kind of field again evolved, okay, which was, so then it evolved. So it is still evolving. Like previously we had shallow networks and there were so many algorithms like backpropagation algorithm, and other algorithms. But now, of course, we have evolved into deep neural networks, okay, and the deep neural networks are so many like convolution neural networks. They are for image processing regulation. Now we have come from a deep neural network, what called LSTM network, long short-term memory network, which try to find the trend in the data, and if the trend is not persisting, then it forgets that. So that is also evolving, and we like nature-inspired computing. So now the question is, when we are designing these algorithms, we have to know the architectures, like how many layers should be there in the network, what should be the weights of the weights which represent the connection between one neuron to the other, which we call synaptic weights in biological word. So how their weights should be this and that. So you learn these algorithms, but then I shared one slide where you can neural network, we trained it by like an evolutionary programming algorithm, genetic algorithm. So, and then when we design these things on these network, how many layers it should be of this kind, this one, there is no standard rule. They just try to fix up which one gives the best result. but we can incorporate nature-inspired computing, like one of my students who just did a dissertation last week. No, he used this transformer network, but he tries to optimize the hyperparameters of the transformer network, which means all these various functions, and using bio-inspired computing techniques of artificial immune system. So why don't everybody does that? Because no, I don't know, it was my passion when I came here. I started a course called biological inspired computing, okay? And I try to do that in interest, but not in every campus it is taught in that fashion. So that is also, many people are not familiar, but definitely this field exists that way, because we have these journals, but and you can incorporate these things into that. So this can be like a hybridization. How do you use the nature-inspired computing to optimize the various machine learning algorithms which are coming up?
What are the greatest barriers to implementing these in widespread?
What is the last?
What are the greatest barriers, challenges to implementing these across wider spread fields like the medical industry, or
Like what?
like the medical industry, or civil engineering, or mechanical engineering?
I think that is what the civil, you can use this for civil engineering. You can use it for mechanical engineering. For example, now as I showed you the example, now that designing this crane system like an elephant trunk model. So they do that, like, polymer design, whatever they do, lotus leaf, all this water resistance fabrics for swimming and all these things they already do. And then they also said nanoparticles, they have designed a spray which they try to spray it on the doorknob so that, it is kind of repellent during COVID time, so the bacteria doesn't stick to it, or something like that. I have heard, I have not seen that. But many people are doing that. So it's not that it is not existing in civil or in mechanical things. I know there is another algorithm called termite algorithm. That is based on how the termites will build their houses, you can say. And in olden days, I know that many people in Iran, they used to use that kind of system for cooling their houses, if taking inspiration from that. So it's not like that. So I am just wondering, we also do, when we don't know about optimization, we don't know how process optimization, you have to do this thing of this thing of this thing of this. How can you fix them together in intelligence? You don't have already. So you can extract that intelligence in the form of what we call explanation intelligence. That, of course, I didn't explain it with that, but that rules tell you what kind of intelligence is exhibited in that particular model. So you can extract that and try to implement. So barrier, I don't know, because whenever you do these things, they become computationally more intensive if you want to see that barrier. So you will need a high processor, a GPU, or a IO supercomputer. You have to log on to it, okay? So, and other thing is, like most of the civil engineering people, not everybody knows about bio-inspired computing, okay? So this is not, so you have to know both the fields in order to do that. Most of the people do their siloing work, in one field. So it's like, you have to know that. I hope I answered your question.
Everybody here has experienced the COVID virus and the vaccines associated with them. The vaccines were developed in a very, very short time. Do I understand that there's a possibility that some of the things that you're talking about today, like connections to nature, algorithms, have something to do with the rapid and important development of these vaccines?
No, because vaccine development, I believe, is a very standard methodology. Most of the biotechnologist people know. So how do we develop a vaccine? They try to identify the virus, and then they see, whatever their lock and key arrangement, and they try to create an antibody so that it nullifies that. Lock and key matches that, and whatever the surface is, they had barriers, so neutralizes that. So So my question is, the artificial immune system, or what we call clonal selection algorithm, is taking inspiration from that algorithm. But we try to implement for our engineering problems, but inspiration comes from that. You said that, yeah, they did it because vaccine making process is very well known. How the human body's immune system work is very well known. But how that method is applied to engineering problems, that is not very well known, or that is not very well widespread. So we try to implement that model and try to apply and to various engineering problems and try to show that this model gives you better result than whatever previous things we have been doing.
The COVID vaccines are the outcome of a development of more than a decade. It was developing that whole process for administering a vaccine, and then it was seemingly quickly applied to how do I customize that for this COVID infection. But there's a decade of work before that that made it possible to do it quickly.
Thinking about the description of the bees' activity and the wolves learning from that pattern, is there work being done on, that's from existing activity, work being done using those algorithms to predict activity of the bees and wolves, and then comparing those results and refining the algorithms to enhance them, or is it only on past activity?
What did you say? No, in past activity? No.
When you originally developed the algorithms, you're observing the existing activity of how the bees communicate with each other and so forth.
So I don't. So I did not evolve genetic, the gray wolf optimization algorithm. Okay. So I have seen this algorithm has been proposed by somebody, Mir Jalali or something like that. It existed. He formulated that algorithm, that this is how you should try to define this problem with this. And many people come up with like we came up with a modified clonal selection algorithm that was an improvement over an existing clonal selection algorithm. But this GWO gray wolf algorithm existed. So it can further be improved. If you say, if I try to do this search mechanism by this equation, this thing, it can further improve. But I exuse this problem. This is published in IEEE transactions journals. So we followed this algorithm, but it was not applied to these problems. So we tried to use that mathematics to apply to this one, which I shared with you. So the thing is, those algorithms are there. You can always improve upon them, like we did it a clonal selection algorithm, and then we proposed a modified clonal selection algorithm, which was basically like a clonal selection algorithm tries to make antibodies for all different antigens. So, but we tried to make it modified, like whichever antibody has the highest fitness, that will be cloned more. We will not have equal number of antibodies for all the antigens. We will make them proportional according to their fitness, and that gave us better result. So you can always tweak with the algorithm, come up with a new mathematical model to that, and also you can also apply that to different platform of problems.
So I've heard stories that the Cleveland Clinic has one of those special supercomputers, and that people are looking at how they fix different types of cancer problems really quickly. Is this the type of thing they're doing? Are they applying the genetic, or are they trying all of the different types of solution ideas or biomimicry that you're talking about? I'm just curious because I've always heard that one of the best uses of AI is going to be how they solve medical problems like cancer, which are very specific. And I'm wondering if you're teaching people to work on that, or if that's a whole different field.
No, I think no, they're doing how they try to treat cancer. That is more of a biological domain. I am not familiar with that much, so I cannot speak about that. But supercomputer, maybe they want to, because there are so many types of things. Sometimes they do gene therapy to treat any condition, how they find out what they do. So maybe first of all they develop these models, so they need a high supercomputer because they are computationally intensive. And we also try to sometimes connect with a higher supercomputer which is located in Columbus if you have to do high computation. Otherwise, you need desktops with very high GPUs so that you can process them. But I am not familiar with that, what they are doing. In machine learning, I know sometimes people have what they do, they try to do model for survival analysis, like some of the data patient die, this one, when they're missing, they don't know, they try to build models for survival analysis of these patients with kidney transplant or other disease. But I don't know when they are doing cancer cure, what methodology they are doing. I think they are trying to develop some drugs which will nullify those cancer cells. They study that particular cancer, what is the shape of that cell. I don't know how to nullify that. That may be one other possibility, but I am not familiar with that.
Okay, and you're training what, general computer science engineers?
Yeah. I'm housed in the College of Engineering, Electrical Engineering and Computer Science. So I offer this course, like biological inspired computing, which I, of course, started there. So after my interest, and then I see where it can be applied to the engineering problems, I do that.
Yeah, great, thanks.
Just a couple comments. I mean, you've got some good examples of the electrical grid and how to optimize certain things. But what I don't think you have is the uncertainty of the future. That Texas had several years ago, a huge system outage because there was a sudden change in weather that took all the wind turbines off the line, and they didn't have enough reserve capacity. So what they've done is say you have to account for the weather forecast 24 hours ahead of time. So today I have to account for tomorrow's forecast of wind energy production. But that goes into everything in the electric grid. There's a time factor. If I lose a power plant and have to bring another one online, just a fossil fuel power plant, it's a minimum of 8 hours from cold start to operation. So I have to have enough excess generating capacity, spinning reserve, to let me lose something and bring something else back on. So that adding that uncertainty of the future, hugely complicates what you have to do and means that your operation efficiency won't be as good as the assumption of instantaneous power. It just complicates how usable this is, but it's still very usable. The human or the medical applications, I have a son-in-law who intends to become a doctor. He's done his undergraduate. He's got a degree in applied mathematics and biology. His goal is to join the workforce that's just developing for being able to model the human body reaction to medicines as medicines are developed, because you can greatly shortcut the development process if you can do that. You still have to do the final testing because the models are never perfect. but the technology is really looks like it would be very advantageous. So your work is helping develop computer scientists that are going to participate in that.
Very well put together.
Thank you very much, Dr. Carr. Thank you.
Thank you.